Hello and welcome. I'm Bill Wake. And we're working this week on Parser Combinators. It's a functional language approach to parsing. And the good side of it is it gives you a very concise, almost grammar-looking statements to parse with. The bad side is, or the challenge is, there seem to be a lot of little corners we're not getting past. And we'll keep going. So where we left off, we had this function that does some sort of type erasure because we had these complicated expressions that yielded the same type, but the whole type was different. Okay, so in our case, we had expression types. It's a tree structure we're building, and every parser was producing either strings or trees. But when you try and combine them, they say, oh, you produced it by listing three things in a row, and this one only has one thing in a row, and that's just not compatible. So this wrap function or wrapper parser lets us basically it sort of hides that difference and just says, look, I'm just a parser returning this thing. I think there's something subtle going on I'm not getting past, so I'll admit that for sure. But what we want to do this morning is, well, morning for me anyway, I want to spend maybe an hour working through consequences of the wrap function that we designed, or the wrap parser. See if we can make it mostly invisible, and we'll see. Maybe this will be adequate. Then I have another paper. Let's see. I can find that. This article, I guess there's a video too, Parser Combinators in Swift. It takes a very, I would call it Haskell approach. I don't know if it's really Haskell, but very function language kind of approach, down to lots of operators and talking about monads and stuff like that. So I'm not quite I'm not up to speed on how this one works. I skimmed the article and said, okay, it looks like it's a different approach than what we've done. We'll give it a go and see what we get. The issues, well, okay, the expression parser, that's good. Interesting. Okay. Well, anyway, we will take a go. He took the same example we're working on, so that's a good thing, and we'll see if we can relate what he's done to what we're doing. In the end, and I may find one more parser example. Paper that describes one of these. We'll kind of try and replicate it, and then we're going to try and take out the parts that work for us and see if we can make our own parser that is good enough to work with my basic interpreter and soon to be compiler. Okay, let's see. So we're back here. All right, so let me see. Let me catch up a little bit. So what we did, let's just start at the top. Okay, we have an expression type. Indirect enum says it builds up tree structures. So you're either a number, which is a leaf, or you're composed of some sort of operator like plus and two children expressions. So I think we have an example. Yeah, maybe not. Well, towards the bottom we're doing it. Yeah, let's come back. Okay, so that's the output type we're trying for ultimately, and it's the analog. So in our grammar for the basic interpreter, we had statements was kind of one high-level operation, and then expressions were their own little their own little structure. Okay, and so we also had a statement type, but expressions bring out all the interesting points I care about at this point, so we're just focusing on that. But if we had a parser combinator based parser that could produce expressions more or less like this, I'm hoping we can just plug that in. I mean, it's maybe just is a little doing a little more work than it should, but I'm hoping we can find a way to refactor from one parser to the other. That's probably the way to say it. All right, then the parser itself. Well, one thing is we have the notion of a parse result. So over some type element, either the parse succeeds, and I tell you the position in the string for the rest of the parse. So the element consumes everything up to that integer, and then after that point, that's where you should start parsing some more. Or you could have a failure. I didn't match this, and I'm going to backtrack. All right. Now the parser, we're saying it has a target type, which is basically this element type. And what it does is it takes an array of characters and the starting position, and then it produces a parse result, which has the ending position or the next starting position. All right, then we can write a parser. So we wrote the match parser that matches strings, and we let it match one character or a range of characters, so 0 through 9. And the way you do this is, given an input and a position, if you're already past the end of the input, then you failed. If the range, like 0 through 9, contains the current character input position, then we return the current character wrapped in a string and position plus 1, saying next time you parse, you should pick up after this character. And if you didn't contain the string, you tried to parse an ampersand as a digit, we return failure. So this is kind of the minimal base case. If you think of induction, I guess, mathematical induction, you have a base case and then you have these, how do I prove if this contains that, or a recursive type of some sort, this is the parser at the leaf. Okay. And I mean, you can define more kinds of parsers like that, but everything else is a parser that takes parser, which in other words is a combinator. So this one is the wrap. Let's see, is that the best place? Let's start at OrElse. Okay, OrElse is trying to say match this or match that. And so you have a P1 parser 1. I don't have a refactor here. Okay, P1 is parser 1 and P2 is parser 2. They both have the same result type. So this combinator takes them, this or that, and when it tries to parse, it basically tries the P1 parser. If that succeeds, it returns the result. Otherwise, it returns whatever the P2 parser does, which either succeeds or fails. And that worked out pretty good. I mean, okay, so W1, W2, they're single character matches. So EX1 has the type, or else, well, wrap, match, target. Okay, but in any case, it demonstrates that we can compose these things. Okay, now we use this symbol to mean or in the grammar sense. I don't know. I probably could overload the regular bar maybe just by itself. I don't know. Would that look better? But we'll see. There's reasons to live with this. Okay. And the way that works is if you have two parsers, it's an infix operator. So this bar symbol, give me two parsers, and I'll put them together with an OrElse. Then we tried this little experiment. If the two parsers, if one's an OrElse and one's a P, then we're going to try and wrap them. I don't know if that was a successful experiment or not. We'll see. That's one of the things we're going to look at today. Okay. Then the and then parser, it says match an A, then match a B. So up here, the interesting thing is it returns a pair, a tuple of the first parser's result and the second parser's result, which means if you're parsing 3 or 4 or 5 things, you have this deeply nested tuple that, with the result parser 1 way on the inside. Okay, and matching A then B is pretty straightforward too. You try and match A, the first parser, If that succeeds, you try and match the second parser, and if they've both succeeded, then you return success, and there's your ordered pair and a position. And if one or both parsers fail, well, if one of the other parsers fails, we return failure, and we give it an operator like this. I don't know. I'm leaning more like less than star greater, kind of more analogous. And also we have the notion of we haven't implemented it, but there is a notion of I don't want to see the left-hand side, or I don't want to see the right-hand side. So I could do those. I think I might switch over to that. And I think this paper uses that style too, something like that. We'll see. Anyway, we got parser, two parsers, and we got an operator that says, okay, if you get both parsers, that's an and then. All right, and now a couple helper functions: make number, give me a string, which is really just a digit at this point, and I will wrap it up in a number. And then this make number middle is if you give me a string comma string tuple with another string tuple, I'll produce an expression by pulling out this item. Okay, so this was customized to match left parend digit right parend. Okay, and you can see this is the result of nesting, of three items in an and then sequence. So it just builds deeper and deeper nested expressions. Really annoying. I don't know. I feel like there's a way around it, but we haven't got there. All right, and then a make op that says give me a string, an expression, and another expression, and I'll build an operation. So this could be plus and E1, E2, two other expressions. Okay, and here's another form that deals with complicated right-hand sides. Okay, you can see this is becoming ugly because of that. All right, let me go back to the wrap thing. Okay, because of the complexity of these things, like you saw, one was like OrElse of wrap, of this, of that. Those types, we're working in the type domain, and it's hard to keep track of the levels, I think. There's a level where we're actually running the parser on some input and getting a tree, the expert type. And then there's the type of this thing in terms of the Swift type of things, and that's where things got messed up. So this function, this wrapper class, its goal is strip off all those types and just end up with a result type that looks right. Okay, and I don't get it why it works. All right, so all we're doing is we're saying, to create this thing, give me a function, and maybe there's something to that. Well, give me your parser, I'll pull out the function and save it. Maybe that's what's doing it. We've lost the class. I guess that is what's going on. We've pulled something out of the class, just this parse function. Let's see if I can get that on one line. Okay, we've pulled the parse function out of that parser, which could be a complicated type, but now we just say, oh, I'm just a little old wrap class that parses this and produces a result. Okay, and then when you parse, all you do is apply the function, parse function. All right, one more piece. Sorry to. I hope it's helpful to you, but it is also helpful to me because it's easy to get lost in this. All right. Then this last function I call it apply, or parser. And this thing's goal is you give me a parser and a type that you want to map into. And I'm built over those two things. I want to know those two types, the parser and a type you want to map into. Then you're going to give me the parser and a map function. the map function goes from the target type, so expression maybe, well, actually string, to the new type, expression. So our make number, you could call digit pipe to apply a digit to make a function, an int constructor, I guess. Let's see. I think I might have an example. Yeah. So here we have digit, which matches one character 0 through 9, and you pipe it to make number. And that make number function we had before, I think I don't even need this stuff. That's boilerplate. Okay. The type of this is apply match expert. So it's taking the parser and the function. It runs the parser. Let's see if I can get to that code. It runs the parser on the input. If it succeeds, it applies the function to the value. So our parser here, if it succeeds matching a digit, then it's going to call make number on that and get back an expert type. And again, the parser, this ends up being the type it produces, expression, well, parser result of expression. All right. And so that gives us the ability to switch domains of things. So even though we start out in the character or string domain, we can get into our expression domain and build some expressions. Okay. And what we have here, okay, look at these types: apply match expression, apply and then match expression. Okay, when we want to combine them, if we just said this example 5 there, okay, it's going to complain at some point, error type, okay, because one of those was a match and one of those was a pipe of a match of a match of a match of a whatever, or and then, because it has 3 things concatenated together versus one thing by itself. So in the types, to the type system, they look different. So what we do is we can wrap them. So if you wrap DN and you wrap PD, then now their types are going to be compatible. Now this is the weird part to me, why I felt like I didn't really understand. Okay, this thing is wrap of, well, it boils down to expression, LLDB expr 69 dot expression. Well, that's our declaration of expression. So this thing is an array, takes an array of characters and ints and produces parse results with expressions. And both of them have that same type. So now they're compatible, and line 190 is perfectly fine. Okay. It's also perfectly ugly, right? We don't want to have to say wrap all the time. I don't know if that's the goal for the rest of this hour. So one idea I had was you would define some sort of operator that's postfix, and then you would say, you would say something like equals dn bang bang or pd bang bang. Okay, this won't compile because we don't have this operator. Or you could inline that like this. We'll have to make sure the precedence of this is right, but I can certainly parenthesize. Or this mess. And let me just kind of format it a little. Okay, so digit pipe to make number, bang bang says wrap that whole thing, and match digit, left paren digit right paren, wrap that whole thing. And it's a little ugly to have to do this, frankly. Um, so I have no doubt we can define an operator that does something like that. What I'm not so sure of, well, I would like to avoid it if possible. Maybe that's the way to say it. And we took a go at it with this wrap operator, the OrElse. Okay, I'm going to pull OrElse down. Okay, so, well, no, I guess I can't pull it down. Right. So what my experiment was, I wanted to say, like, what if this operator did this for you? If you already had an or else, oh, I can see why no. Okay, yeah. So this one is saying, I'm hoping that's the real thing. I'm hoping. um, so if you just have two parsers, let's just let's just wrap them in an or else. If you have an or else and another parser, or else a p and another parser p, then we want to wrap them. Well, and I think that may be the problem with that theory is it's going to do an or else. It's only going to apply once. So if I do W1 or W2, well, that's not a real example, is it? Let's see. The result of this is an or else, but the type is going to be wrap of something, wrap of p.target. Okay. And so this is never going to apply the second time because it's not going to find a wrap on the right hand side. It's going to find a p.target. And that's not going to work. Now, I don't know if it applies it. Let's see the type of W1. Wrap match. Wrap. Okay. Yeah, they are not. Well, this is. I think like wrap. I'm surprised it knows all that. Okay. But EX3 works, so let's see what it's producing. Oops, it was what it was producing. Okay. Array character int goes to parse result string. Array character int. Now, or else. So I guess that's the two arguments to W1, W2 maybe? I don't know. Okay, or else P is already a P. Okay. What can I do to P1? Or else 1 and or else 2. Let's just get that much information, I guess. Or else one, or else one. Okay, so I'm not calling this operator anywhere. Let's run the whole thing. I'm never calling that wrap operator. Okay. Well, that's sort of interesting. Why? Okay. What confuses me is I think okay, W1, W2 calls or else 1, and that produces an or else of W1, W2. Okay, that is fine. That's an or else W1, W2. I would have thought, well, it's or else produces P dot target. Okay. Why is it not triggering? So I would have thought that the result of W1, W2, let's my 1 equals W1 or W2. Now, I would think that is an or else, yes. Okay. With the two pieces. Okay. And nothing but an or else. Okay. So two or else's with a parse result of string, which is what W1 matches, is a wrapper type. Now, if I take my 1 or W3, or else wrap match target. Hello. I've got a guest. Okay. I'll see you later. All right. Yeah, this thing is complicated. All right, let's see. This is wrap match target. W1, I think, is wrap match target. Let's try this with W1. Operator is not a known binary operator. So the types don't match. Oh. My 1. Well, what if I wrap here? Is that going to work? So wrap a P dot target. P and or else P target be equivalent. Or else. Do that for a minute. Okay. If I have two parsers, I don't know. I want to say wrap. I think I want to say wrap of p dot target. Is that not legal? Wrap of this, that. That's what I think it should be. Let's stop and run. Okay, that seems legit. Let's take this one out, because I don't think it's happening. Stop and run again. Okay. Now that seems okay. Let's let equals. Let's go down where we were towards the bottom. Let's see if this one works now. Oh, ambiguous. But 4 is fine, huh? I asked a friend if he had any suggestions on this, and he thought there's a new keyword any that might be what we need. I don't know. So it looks like my OrElse producing a DN type. Okay, let's get these again. DN apply match expert. This thing is that. Can I wrap the ins? Would it help to wrap the insides? Those are the two things that need to be wrapped, right? So maybe that's where my focus should be. And the result is this anonymized type that's an OrElse, so it's neutral to anything else, I hope. Okay, let's see what happens. I think we commented out X5 again. Yes. Oh. DN apply match expert. PD apply a bunch of stuff. Oh, more context. I don't think it's an issue of parentheses. Sorry for the background noise, by the way. Hope Mike's not picking it up. Okay. Still ambiguous. Why? Type of expression is ambiguous without more something. Context. What would... Not the buttons. Okay, so I don't know what the context would be here. Wrapping them is okay. Maybe they don't have to be the same. Okay. OrElse. P1, P2, and then the type is what? Is the type? It's a parser. I feel like I'm close to something. Okay, so we had our and then. It has these two types. Okay. But I want to say, okay, let's try modifying this. All right, so I'm going to comment out a version. Whoops. Wrap match or else. Okay. And this will be what we had. Okay, I'm going to say, what if OrElse takes a P1 and a P2? And produces a parser. The target is P1 dot target. I think it's going to be a wrap of P1 dot target. Is that legit? Wrap of E. Okay. P1, P2. Okay, and then I want to say, I don't know if I get a where clause here, where P1 dot target equals I think it's just equal P2 dot target. P1, P2, parse result of wrap of P2 dot target maybe it's a parse result is it is equals okay. P1 dot target since they're the same target types. Okay. That's okay. I have no wrap here. That's the only one that didn't work. Okay, 223. Okay. But otherwise, you're going to run. Is that the deal? Yes, it is. Okay, but I didn't do any wrapping. Have I changed anything? I don't know. How do I get a wrap in here? My operator wraps everything. Okay, I don't think that's helping anything. I don't know, everything's wrapped at this point. Like, what's your problem? Let's see. Down here again. This is the match, apply match. This is apply of a complicated thing. DNW wraps DN. Okay, we can either, I guess we could say it this way. DNW wraps that. If you wrap it, it's fine. Whether you wrap it directly or in another, put in another variable. But DN, let's see, DNW. See, it says it's this complicated wrap target. But I think it boils down to expr. So I think wrap of all that dot target is expr dot target basically. And DN, that's apply. Expr. Yeah, they're already okay if they're wrapped, so I'm not accomplishing anything. More's the pity. Okay, wrap. I'm going to take off. Let's put this function back. Let's take this one out. Because I think it boils down to the same thing, where P1 is P1, P1 is P2. Okay. Now this, let's peel off what we can. This should run. Oh, I took out the prints. Everything should have values. Yep. Now, I want to take out some wraps and see what we get. Okay. If I take out this wrap, does it work? OrElse P. Really? I don't know what that is. Cannot convert value. Expected type. So I'm just going to put these back. Okay. P1, P2, P. Conflicting arguments to generic parameter type. Okay. Let me revert. Did this work? Yeah, let me reset. Okay. OrElse P. Let's take out this one because I don't think it does anything. Oh, does it do something? Oh, it does do something. Okay. So that does allow this one wrapped value. This is wrapped once, wrapped twice, wrapped 3 times. And that takes care of that. Okay. Let's I don't know how. Let me try. Let's try and do this operator. I think it's multiplication precedence. I don't know. This operator bang bang. P1. I guess it's just P of parser. Goes to wrap of P. Okay. Here we must have a. Oh, I wanted postfix. Target be equivalent. Only infix operators. Okay. Postfix operators. Okay. I gotta choose a new name. Question mark was such a good one. Exclamation. Can I do that? Would seem ambiguous. Okay. So now let's try this thing again. Gotta be separate from its operand. Oh, really? Huh. I didn't know that. Expected expression after 217. Interesting. After operator. Okay. And and we want to do this kind of in one statement. I think I'm going to have to parenthesize it. Example 8 equals this dot dot. Don't need that stuff. Or this dot dot. Right. Do I have to put on one line? Operator is not a no operator. Looks known to me. Why is DN happy? Line 204 is happy. Line 206 is not. And DN is just digit or make number, pipe make number. Digit pipe make number. Let's take this off, make sure that's still okay. Oh, now it's okay. See, I don't know. I think there was a glitch in Xcode there for a minute, the playground. All right. And so ex8.parse of 7 that array success number 7 by itself. Okay, that's the expression. And 3 is the position. 0, 1, 2, 3 at the end is where it should start. Okay. So I think we've demonstrated that the binary operator can, I'm sorry, the postfix operator can make up for these wraps and make them a little less obnoxious. Only a little. I don't know why. I don't know why putting the wrap inside didn't do the job. I don't know. I'm sure if I had it, it would all look plausible, but getting there is not happening. All right. Tell you what. Let's save this. Let's check it in. And push. Okay. And let's take a break. About 3 minutes. Yeah, top of the hour, we'll start back up. And we'll try this other parsing approach and see if that goes any better. This is okay. I think this can work if we have to, but we'll give it the other one a shot. All right, see you in a couple. All right, welcome back. So we're going to create yet another playground. Parser Com 2, I guess. I don't know. And we'll do an initial check-in. All right. So parser combinator. So this should all kind of be simple or familiar at this point in a way. So we got a parser. It takes, in his case, he's done string to result type and a string, and he made it optional. So it's optional. If it fails, it's going to be nil, and if it succeeds, it'll give us the element we parsed and the rest of the string. All right, so let's create that type. Whoops. Okay, maybe I can't copy from there. Good, okay. And let's make this a little more visible. Oh, and let's get to do going here. Okay, so PC-22-04. So type erasing function, we really got that last time. Okay, these are just kind of notes, I guess. What else we did? What we did today is try to automatically wrap arguments and or result. Didn't really take, and that could be me. And then define a postscript wrap operator. And maybe it should be like kind of to match the others. Yeah, I think it probably should. Okay. That's not done. All right. We're trying approach. I guess it wouldn't hurt to put the link in. Okay. And we've got the parser, the definition of a parser, and container of a closure, right? So the function is the thing that the struct contains. Okay, now he has this function pure. Let's see what it's doing. So pure A, it's got a parser. Basically, it's returning A, isn't it? So it's like an identity function. Let's take it. Okay. Oops. pcom2. Okay. So this function creates a parser. So again, we're kind of creating parsers. That's okay, rather than being parsers. So it's done on the function level instead of the class level, like the other solution. Okay. The parser it creates is a at whatever position you, whatever you gave it. So it's kind of like injecting a value at the front. Okay. So the string, the input string is $0. We're not touching it. We're just inserting an A in there. Okay. And then the next one is empty. And this one says, I fail. Okay. So it returns the nil saying this is a parser that always fails. Okay. Now, this is this is where I've got to we're going to have to understand this one, or I think we're not going to understand the whole thing. Okay. Given a parser of some type and a function. Okay, this is kind of like our map function thing, I think. Give me a parser and a function from the value to a new parser. That's different. Okay, let's make a new parser. Okay, so the parser we return is if we get a result. Okay, yeah, if this thing return succeeds, then apply the function to the result and parse the rest. Oh, this is definitely interesting. Okay. The function goes from an A to a parser. Okay. Wow. Let's All right, let's call pure of C. Missing argument label A in call. Okay. I'm not going to make you name that. Okay. I don't know the precedence of this thing. I'm just going to say addition. Okay. Escaping closure requires. Is it here? Okay. Okay. So. Pure C is a parser. PC.parse applied to X, right? Oh, it did come back. Okay. Okay, so the result of parsing pure C is a C character result and the rest of the string untouched. Okay. And then this, we have to give it a function. Sorry, it's the result. It's got to convert an A to a parser. Let's do pure C. Pure 9. Dash pipe 2, or what do you call this? Bind. Apply the function to the result and parse the rest. Eight. We want a function on the string the input is an A, so it's a string, and the result should be a parser. We want to go from a string to a parser. Let n equal int of $0.
You see Grandpa's cup, huh?
Hmm.
I'm sure you can spare that one. Did you want some water?
Let's defer this one a minute. Okay, but I'm going to have to understand it. I wish I did. Fmap. Condition precedence. Okay. Let's give you parameter. Okay. Let's see what he says here. You receive the input, you see the closure, and the input is passed as an argument. Parse that with a given parser. Okay, if it succeeds, you get a tuple, you extract the result and apply f. And that f is the result of the second parser. Use that parser for the main input.
Did you bring his plank upstairs so I can come upstairs? Are you gonna walk upstairs, bud? Or you need to be carried?
You can immediately get the functor fmap. Okay. P. A function from A to B in a parser of A gives me a parser of B. Okay, so fmap seems useful.
And he tells me
If we take A,
it's nice he steps back because you're tall.
we take a function. Let's try it. Okay, a function int of $0. And a parser A, pure 9, is pure, returns me a parser. Okay, so I think I'm going to get a 9. I don't know. A 9? String goes to optional. If I say x1.parse applied to ABC. Okay. Oh man. Still got formatting issues here. Okay. It looks like it's 9. So it's the number 9, and the rest of the string is ABC still. So this function got applied to this parser. So it applied the function to the 9 that came out of the pure parser and gave us back the rest of the string untouched. Because that's kind of what pure does. Okay. All right, let's keep going. All right, so alternative choice operator. This should look familiar. Parser input in. If the first result succeeds, return it. Else return the end of the rest. Okay, that's kind of pretty close to what we did in the other one. I mean, we would expect it to be similar. All right. And addition precedence. Okay. If you apply A to two parsers returning A, you get a parser returning A. The generic stuff is definitely working better than what we saw before. And you return a parser that reads the input, gets a result. If it succeeds, it returns it. And otherwise, it returns this. Okay. That makes sense. I'm not sure about this. Okay. Oh, he's used those same operators I mentioned before. So P byte F and F array Q. Const. The funny thing here is maybe this is where I'm falling apart otherwise. We have a parser from A to B. F and F. Well, I don't know what this const thing is. Well, let's see if this. So this is the difference here, and maybe this is the subtlety I've missed in the other one. But the star says, "Give me a parser of A to B." And a parser of A. This sentence doesn't help me that much. Function application for monadic structure. Sequence. Second one is the left. It tries P then Q. Uses both, but only take the left side output. Yeah, that's okay. I gotta say, this one sounds like the one that maybe is making this sequence operator work the way a useful way. I'm gonna say multiplication precedence. Multiplication precedence, yeah. And this probably needs an escaping. I don't know why not. P parser of A to B. Okay. Okay, I'm not the only one who doesn't know const. Cannot find const. Hmm. Const of ID. Okay, this one I think is fine. Satisfy, you give it a const of true. I don't think you need. Well, I think this function is reasonable. I'm not sure what we're going to do about these operators. Okay, character bool. Uncons. Okay, I'm gonna. So const. I don't know what that ID is. That just doesn't make any sense. Is it the function ID? Okay. F must be the function. Let's see. Does he offer code anywhere for this? Try Parser. Okay. Haskell's greater equal and Swift's flat map. In, out, one, out, two. This is not what we're seeing here. I think he's well, he's genericized over input as well as output, I guess. Oh boy. All right. Looks like he's made substantial changes here. Apply the function of the output to the input of the rest. Maybe we should just do a code read on this. I don't know. Okay, you give me a parser and a function that produces a parser. And I will give you a parser from the original input to the output. Kind of makes sense. Okay, now star is parse the input. P is a parser. Q is a function that creates a parser from nothing. And I don't see where out 2 comes in. Oh, P is a parser from out 1 to out 2. Q produces a parser from in to out 1. Okay, so we're going to try and run the parser on the input. That gives us a function from out 1 to out 2. Then we're going to parse Q on the rest of the input. And return the result. So we're running P. And then run the Q function on the rest. Okay. Parse P input. What's confusing to me is the second argument. I got rid of that const stuff. Okay. Okay, create a parser that runs the parser, runs P on the input. If it succeeds, it returns input 2. What's input 2? If it succeeds, it gave us back an input 2. Okay, we're done with input 2 and the output. Oh, boy. All right, let's see what else we got here. Parser plus arithmetic. What's this? Oh, here's id. Okay, id returns itself. Const returns the constant value. So const of id returned the id function. Const by itself is a function that returns a function. Negate cons. Okay. This is just so very close to a Haskell approach. I know in the paper, let's see where to go. I guess I lost it. At the end, somewhere the performance is already bad. So I don't know if this is just kind of a toy project. It's cool and clever that it is able to implement the Haskell approach, but I'm finding it really hard to follow. There's something deep going on with these two, and maybe we can go back to those. Okay, you give me a parser and a function that goes from a value to a new parser, and I'll give you the new parser. So we take your input, we parse it, we get a result back, and we would apply our function to the result. And parse the rest of the input. I think if I could build up an intuition for this, I think I would learn something good. So where he used it down here, P. Okay, I wish I had a name for this. give me a function from A to B and a parser for A, and I'll return you a parser for B. Give me and that's the same as P bind to A and pure f of A. So apply the function to A, get a value B. Where's the parser come in? Okay, the parser's there. P Oh. I bet you're glad you're not paying to watch me sit here and think about things. Okay, so P is the parser, goes in to that greater minus. I think it's bind. So the function pure of f of A is definitely a parser, but it's a parser that spits back it returns you a value and leaves you the rest of the input. So in a way, it's a way to peel off something, I guess. Okay. Okay, so pure is basically inject a constant, return a constant, and give me the rest of the string to parse. And so this expression takes the A value, applies the function, and says generate that mapped value. And it's a parser. So here we applied the int function to the front, and then we get the rest back. So I think I've got to get a simple matcher working. I'm going to comment out these for now. And let's see, it's this thing, predicate character bool. Excuse me. Let's write a function match, more like what we did before. And let's just take a C of a character, returns a parser of character. Okay, so the parser is takes some input, and what does it do? Well, it's a function from input to pair, optional pair. All right, so if C equals input dot first, well, how about if input dot is empty, return nil. Okay. If input dot first bang equals C, then return I think we want to return C. Return the character and the rest of the input. Input dot drop first. And I guess I'm probably going to have to make that a string to come out right. Otherwise, we didn't match, return nil. Type of expression is ambiguous. Well, we certainly get that enough. Okay, now why does he get to do that? Return parser, predicate of head, return tail head. Type of expression is ambiguous. That what's the type of C? Character. What's the type of this? I think I gotta make this a string. Although they didn't. Head, tail. Oh, he's got his uncons. Don't need the word character. Okay. Part of his performance thing is no doubt, I don't know. Everything should be substrings probably rather than strings, but okay. Let's take this out. Okay. So if I do match of x dot parse of x, let's see if that has a value. Missing argument C. Again, I'm not going to require that. $53. All right, let's take this one out too. We're not there. Okay, this thing matched x and returned that. Let's parse x 1, 2, 3. Actually goes back to 1, 2, 3 is the rest. Okay. That much I can understand. Okay. Now my match function, can I work with that with these things? So match is a function from A to character. Sorry, it's a parser of character. I wonder if it should be a string, but that's okay. And I need a function from character to something. Okay, so takes a parser and a function. Let's try that. the parser is match of x. And the function is string of $0. Okay. $0. Let P1 equal that. Okay. Now P1 is a parser. Oh dear. B could not be inferred. Oh, my function has to produce a parser. Give me a parser. Give me a function from A to a parser for B. I'll run the parser on the input. I'll apply the function and get a new parser on the rest. Okay, let's do this pure thing. Match of X is a parser. M1 is a parser of character. We hope it's a, okay, ambiguous use of a init. Oh, pure wants a function, right? Use init. Pure wants a constant value. String of $0. Okay. I don't understand the concern here. It's That's ambiguous. Pure takes a value of type A and produces a parser of A. So if I pass in a string, gotta find type parser. Character to parser string. Oh, now this thing's happy. No, he's not. There's not a bone barrier. Okay, let's do M2. Type of match X should be parser to character, right? Yep. M2 is a function from character to parser of string. So that greater minus M2 is character. M1 was parser of character. The function is character to parser of string. I don't get the issue. That seems like it's matched to me. What does this say? Character to parser of string. Which is what we expect. Okay, it's a function. What? M1 is that. All right, and what do we expect? Well, we expect the X to be converted to a 9, and then the rest of the input. And I think that's what we're seeing here. Input, X is a string. If we did the same thing with M1, we should get a character back, the X. Yeah. Now, why I can't say string of CH here? Oh, this playground thing, man. Okay, character to parser of string. Now this should change. Yeah, the result is no longer the 9. It's the character as a string. Okay. Now let me turn this into, can I turn it into an int? Int dot. I don't know how you convert a string. Oh, more defaults. So we expect a 7 character. Oh. Cannot convert value type character. Expected argument type string. Try again. Ugh. Cannot convert value of type character to expected argument type string. There it went away. Nil. Okay, something fails. M1.parse7x. M1 is match this. Oh, let's match 7. Okay. Yeah, something's going on here. So, M1 parse the 7. That's a literal character match. Returns back character 7 and the rest of the string. Then this parser converts. So what does it do? It takes the first parser, applies the function to its result. Okay, so converts it to an int, and returns the rest of the parse. It feeds that value to the other parser. So it gives me the character and then returns the pure parser, so that inserts the character in the input or in the output. The character inserts the value in the output. The value is the int, and then it's still a parser. It's got the rest of the input there for you. Okay, so I'm not sure pure is the best parser to be using, but But this function does convert. It's just confusing to me that F2 is this function. All right. Let's see where we are. Okay, so my satisfy, I just did match instead of satisfy. Satisfy is willing to, well, it's willing to take a condition. Okay. Okay. Where I'm left is I can tell there's something clever going on because we're passing in things that return parsers all the time. It's certainly compact enough in the functional form like this. Okay. I'm not sure what to do about all this. And this is cute, a nice little recursive definition. So if you want many of something that's 0 or more, it's either nothing or return 1 or more. And 1 or more says, well, append all these things with many. You got to have 1 and then many of these. Okay, so cute, but my goodness. Okay. And how's it grounded, right? So basically it comes down to this sort of accept an empty list. So that gets you that, and then you cons into it. Now, this whole thing is very concise and everything. I mean, it's a bit of a jewel for sure. This I would call fail instead of empty. So A and pure f of A, given a value, this parser will give you the function applied to the value and the rest of the input. Okay. I'm not sure I'm going to get anything useful out of this beyond what we have for now. It's cute. Okay, expr. Now, interestingly here, I guess it's kind of recursive. Return t and symbol plus expression. Pipe to e pure plus t plus e. So it's calculating a result or just the term value. Yeah, okay. Yeah, so parser, it results in an int. Interesting. It's evaluating as well as parsing it, I guess. So here you can see that operator that only takes the right-hand side because we know the left-hand side is a plus. We don't have to do anything about it. Yeah, I mean, this is nice. It's got this recursion, and we had to do a bind in the other one to make this work, but he can do it here because he's returning parsers instead of just being a parser. So he can return the function. He can call that function and get a parser because it's recursive. So that's nice. That's cleaning up one little bit. I wish I were more comfortable with it, but I think it's an interesting dive. There's definitely some cuteness going on, and it tells me I really do need to go study Haskell. I've put that off. A friend gave me a book like 10 years ago, and I haven't touched it. I don't even know where it is. I'll have to find it. But, it's clear there's little techniques here, this bind thing and other stuff that I'm not, I don't have the intuition for yet. I'm working it through, but I don't have the intuition. So that's a barrier for me. I can see the pieces that are almost like what we did, in some cases, but then we got these ones that aren't. But something clever's going on here, that this is a parser from A to B. So P and Q. I don't think we have an example with P and Q and R. Yeah, we don't have the same one twice. But Carry self to an end. I think, I don't know, Swift changed somewhat since then. Like, we got complaints about adding, maybe it was just for a postfix operator. The nice thing with this, I don't think I have an example otherwise, uh, what this is saying, I think it's saying name. It's naming the rule. No, it's not. What there somewhere there's a thing that you can develop an error message if you're expecting A or B or C. Then you get an error message that's like, oh, you weren't A or B or C, and we can sometimes attach names to them so the error message comes out better. But yeah, I'm gonna throw errors. Yeah, that's the other piece I think we need. And we didn't really walk through this diesel one that we found, or I found. Maybe spend a couple minutes on that. So, where's the source? Parser. Okay. So in this one, yeah, element stream or error, and we wrap that in parse result. You can put a message in the parse result, and we probably need to do that for a realistic one. So, and an error function that has a diagnostic message or diagnostic. That well, we return nil. We modified a case to return failure, but we didn't attach the message. And I think we should, because you get a message if there's a sequence A then B then C, and you had A then B but not C. That's probably worth a message. Now, the message doesn't report right away because it could be an alternative, and you took the alternative. But I think we'll have to include that in our real situation. So it's going to be similar. Here's, okay, combine. Oh, interesting. Well, that's not quite what we need. I'm still the array stuff sticks in my head. Like if you have a parser that produces a type X followed by a parser producing type X, I would like that to be a parser that produces array of X. And we didn't make that happen. This is where we borrow this type erasing because we just pull the function out. Here, parser.parse. Okay. The mini combinator. There should be one for a separator. I don't know if he has that one in this thing. Or else. Surrounded. No. Yeah, that's another one we can do. So maybe I need to just take some notes here. Oh, nice. Thanks for joining. Right. So, let's see. That's today's, and my interpretation of this is heavily based on Haskell. Need to understand binding operator better, and sequence operators are doing something clever to combine parser functions with values. Okay, and then this is for our version. whatever we do. Um, One thing is we need the error reporting. We need to decide um, input string, substring, or position. Or stream. There's the notion of a stream of things. Um, can input be tokens? We have that now. The tokens, if nothing else, they track line numbers and column numbers, but they also do a little bit of context look ahead or something for basics requirements. And the string thing is nice, but I think to integrate with our code, it'll be easier to have tokens. Error reporting string tokens. Can we create arrays of results from a series of sequence operators? That's a thing to make that piece more useful. So A, then B, then C, the type needs to be, it would be nice if it were an array of A, B, C. Also, we'll need operators. We'll certainly need something, well, let's say and. I'm going to say or and. Maybe there's an and and an and. Okay, these are kind of, let's put them separate. Okay. There's an or operator. There's two kinds of and operators. There's a wrap, which I don't know. Let's call it this. I think there may be a prefix operator that's kind of like this. I don't know. It may be a function. Well, many one or more, and then what would you call it? Separated, separated, sep. I want to say that. I want to say a match, comma, or maybe match, comma, and a. But I want that to match one and one or more or zero or more follow, comma list basically. So an a comma a comma a comma a. So think of a subscript. You've got x sub 3 comma 4. All right, I want 3 comma 4 to be matched by this. What other ones have we talked through? We had bind. Oh, we had a map. That thing. And that's a map. All right. Okay. That's the wrap. I think if you had those, you've got something rich enough. The only we're gonna have to work out something. I don't know. Okay, that That's set. So 0 more. I guess there's also an optional. 0 or more, 1 or more, 0 or 1. Those are very common. And then lists of things and alternatives. Bind. Oh yeah, we'll need that bind thing, I think, because the way we're doing it, it would be nice if we didn't. All right, and there may be more, but the realistic one is going to have to do all this stuff. I got to think on this postscript, the list, the match thing with the separators. And that would ideally produce an array of A's. Okay, I don't know. All right, well, I think I'm going to look around a little more research. My friend mentioned this any operator, and it's a type matching thing. I'll see if I don't even know if we have that in, if it's only in the beta version or if it's out there. That may help us with something on this, so we don't need the bind or the wrap so much, rather. But if I don't see anything interesting enough to bring in, I think we'll take our playgrounds and work from scratch to do a more, well, I'll say production ready, but I don't think nobody else is going to use this but me. But build a parser library, parser combinator library that we can use in our interpreter and see how that goes. That may influence some of our decisions. We'll see. All right. Thanks for joining. I don't end up stumbling around quite so much as we did today usually, but we got through the wrap thing and saw some interesting things in that other version. All right, and next time is tomorrow, Friday. It's 10 a.m. Eastern to 12:30 p.m. or 3 to 5:30 p.m. UTC, and I hope to see you then or sometime again. Take care. Bye bye.